Hi there. This video is going to walk through the basics of the variational method, which is one of the approximate methods that we use as quantum chemists. This is a method that is used extensively in computational chemistry. So if you've ever wondered what's happening behind the scenes of programs like Spartan or Gaussian, okay, the computer is doing a lot of variational calculations for you. All right, so the whole reason that we have these approximate methods to begin with, remember, is because we can't solve the Schrodinger equation for anything that has more than one electron. Okay, so once we start moving past hydrogen to helium, adding in one electron, right, all hell breaks loose with those interelectronic repulsions that we can't model exactly, and we can no longer solve our Schrodinger equation exactly. So that's where these approximate methods come in, and this one we're going to talk about is called our variational method. This method is most useful for approximating ground state energies. Okay, so you'll see that it's most often going to be used to calculate ground states. And one thing that we have to keep in mind, or a couple of things that we have to keep in mind in using the variational method, is that at the very least, we need to make sure that we satisfy our symmetry, nodal, and boundary conditions that we expect for the exact wave function. Okay, so if you think to models that we've looked at previously, like the particle in a box, in that case, if you had a system that was kind of similar to that, you'd want to make sure that you had the same sort of symmetry, the same nodal behavior, so that n-1 number of nodes kind of behavior, and similar boundary conditions to that model. Okay, so the basis for our variational method is the variational theorem. Okay, so it's basically a mathematical statement that is the integral of your what we call our trial function. So phi represents some function that we have devised that we think represents our system pretty well. Okay, so phi is what we reference as our trial function. Okay, so it's not going to be your exact wave function, right? That's what we don't know at this point, but it's a trial function that we've essentially guessed at depending on what our boundary conditions are and those other things that we talked about that need to be satisfied, so nodal conditions and symmetry and things like that. Okay, so our theorem essentially takes your trial function and calculates the energy, the average energy, just like we would normally, except instead of your actual wave function for your system, you're putting in the trial function that you have devised. Okay, so you take that average value of your energy. Remember, H is the Hamiltonian, that's the operator for total energy. Okay, and then your denominator is just going to essentially be your normalization condition for your trial function. So if you happen to have normalized trial functions, if phi is normalized, okay, then that denominator is just going to go to 1. Okay, so your denominator is unity if phi is normalized. Okay, so you'd plug in your trial function that you've developed, do this calculation, come up with a energy that corresponds to that trial function, okay, and then the variational theorem tells you that the result that you get for your trial function energy can never be less than the ground state energy. Okay, so E phi, E with your trial function, should always be greater than your actual true ground state energy. Okay, that's essentially what we can think of as basically a law of using the variational theorem. Can never be lower than the ground state energy. Now you could be equal to the ground state energy, right? So if E phi turns out to actually be equal to your exact ground state energy, then your trial function phi is actually then the true ground state wave function. Okay, but otherwise Unless that's the case, you will only ever approach your exact ground state energy from above. Okay, so we always say we're approaching our energy, our ground state energy from above whenever we do a variational calculation. Okay, so the calculation that you're doing is not that involved. Okay, this is all stuff that we've done before. Okay, so the actual mechanics of evaluating that trial function energy or that variational energy is pretty straightforward. So mathematically, this is nice. Okay, there's just a few caveats that you need to keep in mind as you're working with this method, and this is really the big one. Okay, you're always going to be approaching your true value from above. Okay, so the trickiest part of doing the variational method, again, it's not necessarily doing the calculation, but it's coming up with a good trial function. Okay, so there's a variety of ways that you can set up your trial function. You can do a very simple one, and you can do very complex ones. It just depends on what your goals are. Okay, so we can choose trial functions, phi, that depend on some arbitrary parameters, okay, that we call variational parameters. So you'll see some trial functions that have kind of some of these arbitrary parameters that are included in the function. Okay, those generally will give you a better fit, okay, but you always want your parameter to have some kind of physical meaning or consequence if you can. Otherwise, you could include, a billion arbitrary parameters, right, and get really good values of your ground state energy, right, but it doesn't necessarily give you a very good physical picture of what's going on. So we always want to include sort of as few parameters as we possibly can and still get a good calculation. Okay, so if our trial function depends on these variational parameters, that means that our energy also depends on these variational parameters. So your energy will always be a function of whatever variational parameter you've decided to use in your trial function. Okay, so if you are using variational parameters in your trial function, what you want to do is to minimize your energy with respect to each of the variational parameters that you've used, and then that will allow you to, again, approach your exact ground state energy. Okay, so remember, minimizing means you take the derivative and set it equal to 0. So here, what you're doing is taking the derivative of your energy, trial function energy, with respect to your parameter. I'll just say alpha as an example here, right? And then that equals 0. So that's the process you'd go through if you do have a variational parameter. Now, remember, you're not necessarily always going to have one, but if you do, that's the method. Okay, so most of the time we will be concerning ourselves with calculating the variational energies for our ground state systems, okay, which is nice because the energies are, it's pretty easy to get a good energy value even when you have a pretty poor approximation for your trial function. Okay, so it's not the wave functions that we're necessarily interested in focusing on in doing these calculations, although those are things that you can certainly obtain. Okay, so you really can use a pretty crude guess for your trial function, or as we would say, a rather poor guess for your trial function, and end up with actually quite a good value for your ground state energy, which is really handy. So variational method is actually quite forgiving. Okay, so this is why we like it. All right, so basically, doing a good variational calculation really just depends on um, your ability to make a sort of good guess at the trial function. So there's not a lot at stake. Okay, so the last couple things to keep in mind in doing a variational calculation is that if you have a symmetric potential energy, okay, which is the case with our hydrogen atom or helium atom, most of our atoms that we're going to be looking at here, the eigenfunctions have to be either symmetric or antisymmetric, which if you look back at our harmonic oscillator or particle in a box wave functions, those were both examples of symmetric and antisymmetric wave functions. And then the other thing that you want to keep in mind is that your ground state should not have any nodes. Okay, so again, similar to what we saw for the harmonic oscillator and particle in a box wave functions earlier. Okay, so now that we have laid the groundwork for the general process of doing a variational method calculation, we're going to do a quick example where we apply it to the system of a particle in a box. Okay, so you might be asking yourself, why would we bother to do that? We already know how to solve the particle in a box problem exactly, and that is certainly true. Okay, but this is really just an example to show you how well the variational method works for cases where you pick a pretty simple trial function for your system. Okay, so particle in a box is really just a nice way for us to assess how good our calculation is because we already know what the exact value is that we're expecting. All right, so let's dive in. So our example, once again, is a particle in a box. We are not going to use a variational parameter in this example, so we're going to keep it nice and simple. So our first step here is to, again, let's pretend we don't know what the solutions are to the particle in a box. Okay, your first step is to devise a trial function for the particle in a one-dimensional box of length A. Okay, so we know something about our system. Okay, we know that our wave function should be 0 outside the box, and our boundary conditions require that our wave function has to be 0 at our boundaries of x equals 0 and x equals a. Okay, these are all, again, things that we know from our previous work with particle in a box. Right, so we know that our trial function needs to satisfy those boundary conditions. And we also know that our ground state function, wave function, has no nodes. Okay, so our trial functions should also have no nodes between our boundary points. And so you could probably think of any number of functions that would satisfy these requirements, but I'm going to go with a simple parabolic function. So we're going to work with our trial function x times a minus x, okay, for the location inside of our box, so between 0 and a, and then we'll say that our function is 0 outside the box. All right, so this is just our very simple trial function that satisfies our conditions for the particle in a box and does not contain any variational parameters. Okay, so next step is, now that we have our trial function, we want to set up our variational theorem equation and do our calculation. Okay, so I like to approach these calculations in a stepwise form. You can do whatever works for you, but I like to calculate my numerator first and then the denominator and then put them back together. Okay, sometimes, it's not really necessary if you have a simple calculation, but sometimes they get pretty complicated, and it's easier for me to keep track if I just separate out my numerator from the denominator. So I'm going to do that approach. Okay, so here is my setup for the numerator. We have our trial function phi that we came up with earlier out front. Complex conjugate, don't forget, but we do not have a complex function here, so that's not significant for us. Hamiltonian in the middle. Remember the Hamiltonian for the particle in a box is just our kinetic energy, right? Remember we have no potential energy in that system, so it's just our kinetic energy operator, and then our trial function again. And don't forget your dx at the end. Okay, so we can further simplify this expression. Again, bring out your constants out front, and then you can evaluate that integral integrand inside there. So why don't you take a minute, pause the video, see if you can evaluate that integral. Keep your integration skills sharp, and then we'll meet back here in a minute and see what you ended up with. Okay, so hopefully you took a minute to evaluate that integral, and hopefully you ended up with something along the lines of h bar squared a cubed over 6m. Okay, so that's just our numerator. Okay, don't forget we still need to do our denominator. Okay, so setting up our denominator, here we have, again, just our phi star phi, so trial function times trial function, and then we can simplify that a little bit. You can look this integral up in any integral table, so pause the video, take a second, see if you can find that result, and we'll check back in a second and see how we did. Okay, so hopefully you've evaluated that, and if all is good, you ended up with the result of a to the 5th over 30 for that one. Okay, so now all we have to do is put them together. Okay, so in that case we get, I'll change my color here to separate it. So putting everything together, we get a variational energy of 5h bar squared over ma squared, okay, which if we want to compare to the energy that we know for the ground state of a particle in a box, we can rewrite this in terms of h instead of h bar. So we get 5h squared over 4 pi squared ma squared. Okay, so take a second and think about how this compares to our true energy of a particle in a box. Okay, so we know that our true energy, E0 or E1 for our ground state for a particle in a box, remember n equals 1 is our ground state. We have h squared over 8 ma squared for that. Okay, so what we're comparing there is basically we just have to compare the coefficient out front here, right? Put a 1 there. Okay, so compare 5 over 4 pi squared to 1/8. Okay, and you should see that you get a percent difference or percent error of about 1.3% for this variational calculation. Okay, so it's not bad, right? 1.3%. I mean, we had a pretty simple trial function approximation there. Okay, we didn't put a ton of thought in there. We're like, hey, this fits our parameters. Let's see how it goes, right? So pretty good result, just using a pretty crude trial function. Okay, and then the other thing that we notice is that 5 over 4 pi squared is about 0.127, 126, 127 or so. Okay, and then 1/8 is about or it is exactly 0.125. Okay, so the other thing that you notice with this result is that our variational energy is in fact a little bit higher than our true energy. Okay, so we've satisfied that rule of a variational calculation. So if you do this correctly, you're always going to find that your variational result is going to be larger than your exact result. Okay, so hopefully that gets you familiar with a simple variational method calculation and illustrates how pretty effective it is with some very simple guesses at trial functions. Okay, so the last little bit that I'm going to mention here is that, again, we have a lot of different options for choosing a trial function. Okay, the example we just did had no variational parameters in it. There are some where you can include your variational parameter directly in your function. And then there's also the situation where you might have a trial function that depends linearly on variational parameters. Okay, so what that means is, like, let's say we take the general form of that parabolic function that we used in our example before, that x times a minus x. Okay, let's add a term to that. Okay, so if our new trial function, right, has our first term there that we used before, and we've added the next order term, okay, these c's here, c1 and c2, those become our variational parameters. Okay, those linear constants, okay, those are variational parameters in the trial function now. Okay, and then the functions that come after the variational parameters, so these are, we would label f1, f2 plus cn f sub n. Okay, the fn here are known as basis functions. Okay, so that's a term that you'll encounter a lot in computational chemistry. So you'll see that term basis function or basis set come into play whenever you do Spartan calculations or things like that. Okay, so the more of these parameters that you include, the more terms that you include essentially in your basis function, or your trial function, I should say, the better result that you'll get for your calculation. Okay, and then one other little factoid for this approach is that if you square the coefficients here, these variational parameters in each term, that gives you essentially the relative contribution of each of those individual basis functions to the overall trial function. Okay, so you could do your variational calculation with this new trial function that depends linearly on these variational parameters. As you can see, the more terms you add, the more complicated your calculation gets. Okay, but if you do that calculation with just adding that second term to what we did before, you get a value for your energy of 0.125002 times h squared over ma squared. Okay, and that's in comparison to our 0.125 exact energy for a particle in a box. So we have now, just by adding that extra term to our trial function, we get our percent error reduced to 0.001%, as opposed to the 1.3% error we had just using the first term. Okay, so hopefully you can see that adding in those variational parameters does in fact improve your calculation. Okay, so you just have to ask yourself, all right, how much work am I willing to do? How much calculating am I willing to do to get a better result for my energy? Okay, so moral of the story is we can use variational parameters additional terms in our trial functions to get pretty impressive results. Okay, the more flexibility we build in, the closer we get to the exact result, but the price we pay is more lengthy calculations or requiring more computer power, okay, if you're doing these with a computer. Okay, so quantum chemists, if you choose that as your profession down the road, they use dozens, hundreds, thousands, millions of terms in these linear variational functions to get as accurate results as possible. Okay, obviously at that point, a computer is necessary for this work. I would say I probably don't want to do any of these calculations by hand for, I would say, more than 2 terms is about my limit on doing them by hand. But conveniently, we do have a method that we're not going to talk about explicitly, but it is described in your book. There is what we call the secular determinant method, which is a handy method for evaluating these trial functions that depend linearly on variational parameters. So there are some tricks up our sleeves to make that work a little bit easier, okay, but still very quickly you're going to want to be employing the use of a computer for a lot of these calculations. Okay, well, I hope that gives you a decent overview of our variational method. It is one of the most commonly used approximation methods that you'll encounter in quantum chemistry.